we can use the Lewis structures to predict the shape of a molecule. So the theory that determines the shape is a theory that electrons repel each other. So it's the valence shell electron pair repulsion theory. And what it says is that each electron group wants as much space as it can get. So what we're going to do is draw the Lewis structure. Then we'll determine the total number of electron groups around the central atom. The side atoms don't matter. They don't affect the shape. Then based on those number of bonding groups, we can determine the shape of the molecule. So let me show you how it works. Here are some examples of some different molecules. So let's look at these molecules and see how that determines their shape. So the first one, CH4. So that molecule, the dot structure, looks like this. We have a carbon with 4 hydrogens bonded to it. So these are all hydrogens, even though they look kind of bad. So carbon with 4 hydrogens. And so what's important to notice is that we have 4 electron groups. Our electron groups are this one, this one, this one, this one. They are all bonds. So we have 4 bonds, and there are no electron pairs. And so the shape of 4 atoms trying to get as far away from each other as possible is called a tetrahedral. And this is a 3-dimensional shape. Each angle is 109 degrees. It's like a tripod with one sticking up. And future slides show this shape a little bit better, and we'll talk about it more. So if you have 4 bonds and no electron pairs, your shape is tetrahedral. Our next example is NF3, and this molecule looks like this. We have nitrogen with the fluorines. The nitrogen has 2 dots on it. The fluorines all have dots on them, but these dots don't matter because they're not on the central atom. So what we're going to look at is the electron groups on the central atom. So let's circle these again. We have a bond, a bond, a bond, and an electron pair. So again, we have 4 electron groups. This time, 3 are bonds, and 1 is an electron pair. So you see that 1, 2, 3 bonds, 1 electron pair. And so it's the same shape of the tetrahedral, except one of the spots doesn't have an atom. And so visualize just pulling one of those atoms off, and so we have the tripod, but nothing's sticking up. And that shape is called trigonal pyramidal. It's like a pyramid with three corners to it. Let's look at the water molecule. We've seen this one. Water, we have oxygen with a hydrogen and a hydrogen, and the oxygen also has 2 electron pairs. Now, our central atom is oxygen, so let's circle the electron groups. We have a bond and 2 pairs. So again, that's 4 total groups. We have 2 bonds and 2 electron pairs, so a total of 4. So whenever we have 4, we're based on that tetrahedral shape. But now we've pulled 2 of the atoms off, and so now we call that shape bent. So those are our options with 4 electron groups. If we were to pull 1 more group off, then we would just have 2 atoms. And our 1 bond, 2 atoms is the simple case, because that's always linear. It's just 2 atoms bonded together. So once you're down to 2 atoms, it's always linear. Let's look at the 3 groups. Our first example is SO3. So SO3, we have an S, O, O, O. And one of the oxygen is double bonded. The other 2 are not. Now we haven't done that structure yet, but you could do that dot structure. That would be a good exercise. But when we count the electron groups on this, we have 2 single bonds They're each a group. This double bond is one group. So even though it's more electrons, they're all working together. So it's only one group. They work together. They don't need separate space. So we have three groups needing space, three electron groups. And in this case, we have three bonds and no electron pairs. So 3, to get as far away from each other, is a shape called Trigonal Planar. And so this is flat. All the bond angles are 120 degrees. And that's the Trigonal Planar shape. Now, if we were to remove one of these atoms, so for example with SO2, we've done this dot structure. SO2 looks like this. And I did this in red, so let's circle our groups in black. So we have one bond, one double bond, and one electron pair. So what we ended up with is two bonds, even though one's single, one's double, it's still two bonds, and one electron pair. And so that shape is still based on the trigonal planar shape, but if we removed one of those atoms, we would have something that looks like this. I don't have a structure. And so this is also called bent, just like the water molecule. Let's consider carbon dioxide. We did this dot structure, and it looked like this. So that's carbon dioxide. If we identify our electron groups, our central atom is carbon. It has this double bond and this double bond. So it has two electron groups. And the best way for two groups to get as far away from each other as possible is a linear shape. So our angle here is 180 degrees, and it's linear. Okay, so this example, we have two bonds, no pairs. And that often is because you have two double bonds, or you might have a triple bond and a single bond. And that's our linear shape. Now, if we were going to pull one of those atoms off, again, we'd be back to our one bond with two atoms, this simple case. So those are the shapes. There's this table, there's a table in your book that can help you identify the shape, but the dot structure tells you the shape of the molecule.